In this section, we'll discuss about alkene formation by elimination reaction of alkyl halide. Now, we are going to apply what is called Zaitsev's rule, and sometimes it could be elimination of H and OH. But in most cases, we'd show you elimination of hydrogen and a halogen. Here we are going to discuss two different types of elimination reaction that results in formation of alkene. In one case, hydrogen would go from one carbon and then halogen would go from its adjacent carbon, forming a double bond. Similarly, one of the carbon can lose hydrogen and the adjacent carbon can lose OH, and this is how H2O would leave and there'd be an alkene formation. Now, quite often more than one product is formed. In that case, we need to know which one would be more favored. Now, we go by this rule, which is given by Zaitsev. It says that highly substituted alkene dominates as a product. I often use the term highly branched. For example, this is my double bond. If anything other than hydrogen is bonded to the double bond, that's considered to be a branch point. So that means if I have a carbon here or methyl group here, that's one branch point. This gives me the second branch point attached to this carbon. Now this gives me third branch point, and say this gives me a fourth branch point. So if there is more than one possible structures, the larger number of branch points would be more favored. So I remember it like this. Between these two pictures, you can see that highly branched horn looks a lot nicer than less branching. So keep that in mind, and that's Zaitsev rule, that whenever there is more than one product formation, highly substituted or highly branched alkene dominates as a product. We'll give you specific examples. We'll begin with this example where you have CH3, and then you look at here, one halogen has to leave as well as adjacent hydrogen. So now the question is, there are two hydrogens in there is one hydrogen it can leave from this carbon shown with asterisk, or the other carbon on the right side. So if these two atoms leave, H and Br, from the left hand side, the double bond would be, let me show you that, you'd have CH3 and then CH, and that Br is gone, so obviously that would have that C, and then this would be treated as CH3, and there'll be double bond here. And keep that in mind that we always double check all these species. So this is shown in this picture with 120-degree angle because this is sp2 hybridization. So how many branch points we have? Again, your focus would be on this carbon-carbon double bond. This is one substituent group or branch point. This is the other branch point. So altogether, there are two substituent groups or two branch points. So that's why we wrote down here di-substituted product. On the other hand, if this is what happens, that means H and Br, H goes from the rightmost carbon and Br goes from the next carbon, then obviously there'll be double bond in here. And that gives you this product. So you'd have CH2 here and then CH3CH2. So how many branch points we have? Again, focus on this carbon-carbon double bond. You have only one substitution group here, or one branch point. So it's a monosubstituted and less favored. Disubstituted is favored product, and indeed, experimentally, scientists find that there are about 81% of this compound is formed. Now this is another structure in which H and OH is going to leave. Now again, there are two possible options in this case. At least we're showing these two options. Hydrogen is going from right hand side carbon, or hydrogen is going from left hand side carbon. That would result in two different products, and one would give you, if you work on it, you'd find one would give you this product, the other one is going to give you this product. Now let's look at number branching or substituent groups other than hydrogen. Obviously this is the methyl group, one substituent group attached to the double bond, second substituent group attached to the double bond, third substituent group, and this has hydrogen. So there are three substituent groups for left hand side product. Now let's focus on the right hand side product. Again, this is carbon-carbon double bond. We didn't show you hydrogen, but if you want to write down, this is one hydrogen, this is the other hydrogen. This is one substituent group. This is the other substituent group attached to carbon-carbon double bond. So here you have two substituent groups. Obviously, two substituent groups are 2 branch points. 3 substituent group means 3 branch points. So 3 branch points will be more favored, and that's why you have a larger proportion of this product formed compared to the other one. I want to remind you, this is on page 117, that low temperature, relatively low temperature, gives dehydration. Like in this case, dehydration happens. On the other hand, if temperature is very high, like 250 degrees centigrade, addition reaction of H and OH will take place to alkene. So you have to control the experimental temperature in order to get your desired product. Now we're going to do one homework problem where you see application of Zaitsev rule, where more branch points will be favored in the reaction. We're going to do 7.16c. As I said, this topic has been discussed in both chapter 7 as well as chapter 4. So you should be pretty familiar with this topic. So let me write down this question, which said that ignoring double bond stereochemistry, what products would you expect from elimination reaction of the following alkyl halide? So I'm going to draw the alkyl halide, which has a 6-membered ring. So that's a 6-membered ring, cyclohexane. Then you'd have I'm writing down Br, that's the alkyl halide. There's H here, and then you have CH3. Let me write down more explicitly so that you know what kind of elimination can happen. Now this carbon, so this is the question given, and they're asking what products you can expect. Now remember, you should be focusing on the carbon that contains the halogen. So I put an asterisk there, this is the halogen, because that's going to be the leaving group. Hydrogen has to leave from that adjacent carbon in order to give alkene. Now it could be on the right side, on the left side, up or down, wherever you have, as long as you have a different carbon. Within the same carbon, there cannot be any bond, any double bond formation. So this carbon has 3 bonds, so you must have 1 hydrogen. Okay, so I explicitly wrote these hydrogens so that you all understand that how you can have elimination reaction. Since Br is a good leaving group, it has to leave, but in order to form alkene, hydrogen has to leave too. If it leaves from right hand side, so this is the right hand side, let's put a dotted circle. If this hydrogen leaves, then you can make a double bond in here, because each of this carbon would have done 3 bonds. So let's rewrite this product, because I don't want to make it messy. It'll be hard to understand this messy. So this is C, and then you'd have CH. Now you'd have a double bond CH2. So this is the product we're getting if these two leave. Now let's find out how many substitution groups we have, or how many branch points we have. On right hand side they're just hydrogen. On the left hand side there's one hydrogen and one group like this. So that's the substitution group, or one branch point. So we'll call it one substitution group or one branch point from carbon-carbon double bond. Now let's examine the other possible product. Now let's use a different pen so that we don't get confused with the groups which are leaving. Br has to leave. So if this Br leaves, now last time we looked at the right hand side hydrogen, now we'll be looking at left hand side hydrogen. If these groups are going to leave, you'd have a double bond in here. So what would be the final product then we're going to get? It's the following. Let me draw that. So you'd have a 6-membered ring. That's 6-membered ring with carbon in here, and that hydrogen is gone. Now there'll be a double bond. Then that's carbon. We have a hydrogen, and then CH3, because those hydrogens are remaining intact. So you have H, H, H. So this is my double bond. Let me see how many substitution groups I have. This is one CH3 group, and this carbon is bonded by a ring structure. So ring structures are considered to be, it's taking really two positions. One is this side, the other one is this side. So it would be acting as a 2 substitution group. So it'd be 2 substitution group for this ring, which occupies 2 positions of carbon, or 2 bonds of carbon, makes 2 bonds with carbon, and this is the third one. So it'd be acting as a 3 substituent group. And in this case, first case, it was 1 substitution group. Obviously this would be the most favored product in this form, in between these two, and that's called Zaitsev's rule, which goes by branch points or number of substitution groups attached to the carbon-carbon double bond.